Okay, so the number of people joining is declining now, so I think it's a good point to start. Welcome, everybody. It is a great honor to welcome you to the inaugural lecture of the Francqui Chair at UHustle today. The chairholder, Professor David Stern, joins us today from Australia, so there it is already Monday evening. My name is Stefan Bruns. I'm an assistant professor in the environmental economics group, and I have the great pleasure to walk you today through this event. So first, our rector, Bernard van Heusden, will talk, followed by Pete Poles, the Dean of the Faculty of Business Economics. Both of them will provide introductory words. And then the chairholder David Stern will talk roughly 1 hour about economic growth and the environment. And then this is followed by a discussion. So given the size of this online session, I would like to ask you to please use the chat to ask questions. You can do that throughout the lecture and also after the lecture in the discussion. I will collect these questions and then ask them to David in the discussion part. So I would also like to make use of the opportunity to emphasize and highlight the upcoming lectures within the Francqui Chair of David. So if you are interested in these topics, you can find more information on the Francqui webpage at UHustle. And you're, of course, cordially invited to join these talks. Okay, so now I will stop sharing the screen and I will give the word now to our rector, Bernard van Heusden.
Thank you very much, Stefan. I guess you hear me well, huh?
Yes.
Dear Professor Stern, dear colleagues and students, dear guests, it's great to see you all, although I just see a couple of screens, but it feels well to be able to have this kind of interaction with people. Although we are in a global pandemic, it's still quite reassuring to see that this doesn't stop researchers from exchanging ideas, debating the issues at hand, and joining knowledge. Let me start by thanking, first of all, the colleagues involved from the Faculty of Business Economics, the Center for Environmental Sciences, and in particular, the Environmental Economics Group and Stefan Bruns for making this online event possible. I know that the circumstances have not made it any easier, but here we are all. Professor Stern, I would like to welcome you to Hasselt University, albeit virtually. For the next few weeks, you will be part of our academic community, even though there are more than 16,000 kilometers between us. I truly hope that somewhere in the near future, you can pay a visit to our campus and meet us in person as well. Let me also thank the Francqui Foundation. For almost 90 years now, the foundation has worked tirelessly to strengthen higher education and scientific research in Belgium, spur scientific cooperation across borders, and offer many opportunities to young researchers in particular. I'll leave it to Dean Pete Powles to introduce our guest of honor in more detail. Let me just say that the Environmental Economics Group couldn't have made a better choice in nominating an international Francqui chairholder, for two reasons. First and foremost, Professor David Stern is an internationally renowned expert in environmental and energy economics. He was one of the lead authors of the IPCC's, the International Panel on Climate Change, fifth assessment report. He's the associate editor of the Ecological Economics Journal and member of the editorial advisory panel for Nature Energy and the Energy Journal, respectively. 5 years ago, he was elected Fellow to Australia's Academy of Social Sciences. His academic authority has been established through many publications and through avid blogging. I invite all of you to check out Stochastic Trend a recognized top 100 economics blog. In short, Professor Stern's research helps us in understanding pathways to sustainability. This brings me to the second reason why this nomination for the International Francqui Chair is so fitting. His work aligns perfectly with U Hassel's ambition to become a truly sustainable university. By the year 2030, it's a commitment to play our part as a center for education, research, and innovation in helping to achieve the Sustainable Development Goals as set by the United Nations. I know what most of you are thinking right now. U Hasselt still has a long way ahead in fulfilling those high ambitions. And you're right. In order to become a smart, sustainable university, in every sense of the word, much more action is needed on many different levels. We will need to think about our infrastructure, water consumption, energy use, waste reduction, and transportation between campuses, to name just a few things. It will require more than sound bites to succeed. It will require determination and creativity. At U Hasselt, we have both, so I'm confident that we can make considerable progress and that we will be able to balance economic, social, and environmental needs. Needless to say, the university is counting on the expertise of all of you as well. Over the past few years, U Hasselt's Environmental Economics group has forged a close collaboration with Professor Stern. I'm sure that the International Francqui Chair will further strengthen and increase this cross-pollination. In the next few weeks, Professor Stern will touch upon the relationship between energy use and economic growth and development, and between growth and environmental quality. He will collaborate on the role of energy in economic growth and on the econometric modeling of global climate change. His lectures will provide an excellent opportunity to exchange ideas, debate, and join knowledge. So I wish you all an interesting and inspiring time. And to you, Professor Stern, a great lecture series. I really look forward, definitely also today, to the opening lecture, given that I am myself, or am specialized in environmental law. I'm also very much interested in the topics of your lectures in the next few weeks. I'll give the floor now to the Dean, Piet Pauwels. Thank you very much.
Thank you, Director. What can I add to that? Professor Stern, a warm welcome. A warm welcome to the Faculty of Business Economics. Yes, business economics, but with a strong, very strong group of environmental economists. People, researchers like you, who investigate elements of the environment at micro and macro level from a truly interdisciplinary perspective. And I think that true interdisciplinary approach is what links you to this group. What has made and was the basis for close collaboration with the environmental economics group of our university on economic valuation, macroeconomic rebound effect, climate research in general. It is that truly interdisciplinary approach that has been missed and has now, through your work, been appreciated. It is the true spirit of the Center for Environmental Sciences, CMK, of this university as well, where biologists, chemists, economists, lawyer people work together on themes of the world that challenge us, and those challenges are not defined in monolithical domains. They are defined as world challenges that should be approached, should be understood, should be solved, hopefully, through an interdisciplinary approach that you express. This collaboration is not new, It's great that we have somebody as a Francqui chair who is known to the group and the group is known to him. Ladies and gentlemen, David Stearns holds a Master of Science from London School of Economics, a PhD from Boston University, and is now a professor at Australian National University Crawford School of Public Policy. As the rector indicated, Professor Stern is influential in his domain and highly appreciated throughout the world. Today's talk will deal with things that seem not to be going well together. Environmental harm, environmental impacts, and growth. Club of Rome, 1960s, already talked about, well, the limits of growth, because growth comes with externalities, and these externalities cannot be avoided. Is there a paradox or a real contradiction? Will growth result in less or more environmental impact, and of what kind? Well, Professor Stern wrote about this in very influential papers, two of which have been published in World Development with a huge number of citations. And these two papers will be the basis, as I believed, as I understood, of this first and inaugural lecture. Looking at the number of participants, looking at the heritage of our group, this topic is very close to the core of who we want to be as a faculty, as a school, in our research, in our education. The context of sustainability, no, the reality, the goal of sustainability, and the context of business development. That is what continues, what drives, what pushes our research, hopefully to the next level in an interdisciplinary and collaborative approach. In name of the faculty and its faculty members, we highly appreciate your presence, your acceptance of the Francqui Chair for these 5 next lectures. And indeed, as the rector said, we're looking forward to more intense collaborations with the people of the school. We're looking forward to your talk, Will More Growth Result in Less Environmental Impact? Thank you very much for your attendance, all of you. And I now want to give the floor to Professor Stern.
Hello, can you see me? Thank you very much for nominating me for this Francqui Chair and for the very nice words of introduction, and a welcome and thanks to everyone who is attending today's inaugural lecture. I'll just try and am I sharing? I'm trying to, oh dear. There we go, share application, select. That's good. Hopefully you all can see the slides. Yes, they're on the screen. Okay, yes. Again, thank you very much. So the topic of the first lecture is economic growth and the environment. And as Pete and the rector both said, Bernard, that this connects to the idea of the environmental Kuznets curve, which I published a number of articles on, and probably all my work, it's the most cited work. And so I thought it was and a very broad subject, so I thought it was an appropriate topic to give this first lecture. So the question I'm addressing is, what is the relationship between economic growth and environmental quality? And I'll start very broad, and then I'll narrow down in some of my more recent research, which mostly focuses on greenhouse gas emissions and air pollution, though starting off in a much broader, more historical setting to tell you something about how this debate has evolved. And I think Pete just mentioned the limits to growth, which I think was published around about 1973. So the early thoughts in the modern environmental movement, environmentalism, was that economic growth was detrimental to the environment. More economic activity used more resources and was going to lead to more environmental impacts. And also that those environmental impacts would be detrimental to both the natural environment, they would deplete resources, those would undercut economic growth, and also hurt human health. And this Limits to Growth report was famous for being an early example of a computer simulation model, and I think that seemed to give it a lot more authority than it might otherwise have had at the time, as this was a very new concept. And they sketched out the results of their simulation model in the book, showing starting in 1900, ending in 2100. And notice, of course, we're now at about 2020 here, or 2021, about here on the graph, and they were talking back here. So things were growing at the time, but they predicted, their model turned out to come true, that at this point in time where we find ourselves, we would already be seeing declining food per capita, even declining industrial output, and things would be, and pollution would still actually be rising. So we'd find ourselves in a very bad situation already by the year 2020. Seems things haven't been quite as bad as they predicted. In 1992, they did a revised version of this and pretty much came up with the same predictions. So they really didn't revise very much. However, by the 1980s, when we're looking at the setting of limits to growth, there'd been very rapid economic growth in the 60s and 70s. By the 1980s, things maybe had slowed down a little, and increasingly it was thought that it wasn't necessarily economic growth that was hurting the environment. There were a lot of very people who were clearing land, causing deforestation, species extinction, and these people were poor. They weren't actually having, there was population growth, but there wasn't really economic growth in some of these developing economies, and it was people's poverty was leading them to have negative environmental impacts, particularly on land and species and so forth. And that gave the idea that maybe we need to get these people richer in order for them to behave in a more sustainable way, in order for them to use resources more efficiently. It was their low technology, their poverty was leading to environmental impacts. On the other hand, we've begun to see some pollutants decline. And so the UN commissioned this report, Our Common Future, in 1987, a commission known as the Brundtland Commission after its chair, former Prime Minister of Norway. And it had two themes. One is we needed to make the poor better off, so they'd have less impact on the environment. Perhaps birth rates would fall as demographic transition started. And we also needed to find for the richer countries a new, more green path of development. And really all this was possible. And the slogan of sustainable development, rather than being limits to growth, was meeting the needs of the present generation, i.e. providing for the poor and also for people in developed economies, without compromising the ability of future generations to meet their own needs, and not having this kind of limits to growth style collapse of the economy in the future, but thinking that it was important to have development to improve the economy. Improve the environment. So things have swung from growth is bad to growth might be actually good for the environment. A framework to think about this, which was also originated around about 1973, I think, in a paper by Paul Ehrlich and Holdren, very famous names. Holdren eventually was an advisor to President Obama, I think. And they came up with the IPAT model. This is an identity. It says that impacts, environmental impacts, we can account for them as an accounting identity as population times affluence times technology. So the idea here is if we hold everything else constant, if we hold the level of economic activity or affluence constant and our technology constant, and we add people, more people doing the same thing, then surely there'll be more impacts on the environment. Nothing else has changed, just more people doing more stuff. On the other hand, more affluence, higher level of economic activity, if that wasn't using an improved technology, would also, according to this identity, lead to greater impact on the environment. And so this P times A, or what economists sometimes call the scale effect, is really behind part of the limits to growth story, that more economic activity, more impacts. The third term, though, is technology, and basically, if you see impacts growing slower than the total level of economic activity, both population times affluence, then it must have been because of an improvement in technology. So population is pretty straightforward. Affluence, economists often think of affluence as GDP per capita, but not necessarily the only measure, and technology is whatever's left over. So it's an identity, and technology is the residual, which makes this equation be an identity. And these factors, this equation is tautological, it's true. These might be known as approximate factors. They directly account for changes in environmental impact, but of course, underlying factors may be policies, legal institutions. So countries with one legal system might have less impact than another one, and other such factors are more fundamental or exogenous factors that may be education, changes in education and so forth, that might be driving the technology term, and also, of course, the other terms in the model. The technology term, we can think of several things. The mix of inputs. So we can think of energy versus labor versus capital. So we could use more labor and less energy. We can use more polluting forms of energy, like high sulfur coal, or less polluting forms of energy, like low sulfur coal or natural gas, or maybe renewable energy. So we have a mix of inputs. Economists tend to think of this as a separate thing from technology, at least mainstream economists, but it comes into the technology term here. So there's opportunities to shift between inputs, shift from fossil fuels to renewable energy, or from more polluting fossil fuels to less polluting. The output mix is the idea that over the course of economic development, countries start a lot of agriculture, they then shift towards industry and eventually to services, and that perhaps services are lower, having lower environmental impact than industry. But actually, of course, there's been a lot of improvements in productivity in industry and services, whether they are computer server farms or shopping malls, transport. All of these things, of course, are not zero emission. They all involve emissions. But to some degree, the shift towards services might have an impact in reducing environmental impacts. And finally, what economists think of as real technological change, and that's using fewer polluting inputs per unit output. So holding this mix constant, we would be using less energy for a given output, more energy efficiency or more productivity from energy. But it would apply this, and perhaps improving the productivity of labor would also allow us to have a higher output with less inputs of resources. So it's not necessarily just improving the efficiency of the resource use, but the efficiency of the use of all the other inputs as well. Productivity in general is a good thing here, holding the other terms in the equation constant, population and affluence. And finally, so this is the mix of inputs going in, and finally, less pollutant emitted per unit output. These are more the end of pipe technology, things like scrubbing sulfur from coal-fired power stations, but also burning fuels at a different temperature that reduces, say, nitrogen oxide emissions. So these are various technologies that once you sort of fixed everything else, that actually sort of result in less pollution, or eliminating more harmful pollution and turning it into a less harmful product like calcium sulfate in the scrubbing facility. Okay, so this is a framework to think about, and it's a true framework, but the technology is sort of just everything else and doesn't really tell us what is happening to technology and how that is affecting impacts to the environment. So in the context of the sustainable development literature, and the context of sort of simple models like that, in 1994, there was a debate in North America about the North American Free Trade Agreement, which was to produce a single market between Canada, United States, and Mexico. And Generally, economists predict that free trade would lead to higher income in all three countries if they all voluntarily join the agreement. Due to specialization due to trade, and perhaps maybe Mexico would benefit most from having free access to the US and Canadian markets. On the other hand, a lot of environmentalists were very opposed. There was a special issue of Scientific American in 1993. There was an article by Herman Daly, who was one of the founders of ecological economics, and he was very negative. He said, yes, this probably will cause growth, and growth will be bad for the environment in Mexico because Mexico has such high land degradation and pollution emissions relative to its income, and growth in Mexico will just exacerbate those trends, and it'll be a very bad thing. A lot of people were worried about the effects on immigration, so forth, but there was definitely a debate among environmentalists which tend to be negative. Environmentalists negative about this agreement. In this setting, two economists, Grossman and Kruger, introduced what we call the environmental Kuznets curve model to predict what would happen. And this is their model, or a sort of stylized version of it. And ideally, these variables, E and G, which are emissions or concentration of pollution in the environment, one or the other, or it could be deforestation, but I used E for emissions because P normally means prices in economics, so rather than pollution, so E for emissions. G is GDP per capita, probably, rather than the total, and G squared is GDP squared per capita squared. And it's, again, it's best to do these in logs to get a reasonable relationship among many countries. And the idea is we get data on pollution concentrations or emissions in many countries I, in many years T, and we look at, we do a regression analysis to see what the relationship between these and GDP per capita. And this is the, ignoring this term, this would be the effect of growth on emissions, this beta 1. There are, of course, also different intercept terms, constants in each country, and also different constants over time. So this allows technology to change independently of the growth of the economy. So if there's a particular pollution reduction technology, we might capture it by this gamma term here, and find there's a random error term here. And the idea, okay, so going back to our IPAT identity, pollution concentration or emissions per person are either I, the impact, or I divided by population, impact per person. And then G, GDP, is GDP per capita. And then the G squared term and the gamma term here somehow capture the technology effects. Oops. And the idea is if beta 1 is positive and beta 2 is negative, initially, economic growth has a bad impact on the environment in those poor countries that people thought needed to get out of their low economic status in order to clean up the environment. Initially, there may be bad impacts of growth, but if this beta 2 term is negative, eventually there'll be a turning point, and eventually growth would begin to clean up environmental damage. So you're in some kind of trap, as it was, that initial growth was damaging to get to the promised land where growth would actually improve things. An early estimate of the environmental Kuznets curve was this paper by Theodore Panayotou. He coined the term environmental Kuznets curve in his paper. It wasn't in the original Grossman and Kruger paper, but it was in Panayotou's paper this term. And basically, he actually made up his own sulfur dioxide emissions data based on energy use and a mix of energy use and some coefficients of relationship between pollution and those energy use. And then he regressed those sulfur dioxide emissions per capita on gross national product per capita across a bunch of countries he had data on. And what he found was there was a peak in the curve somewhere around about $4,000 per capita back in 1993 dollars, okay? And after that, you went down this curve and your sulfur emissions per person fell, even though you were getting richer. So he fitted this for the data, came up with the result and said this does seem to be something that's going on. It's similar to the results in the Grossman and Kruger paper. Grossman and Kruger pretty much came up with a similar result for at least some pollutants, and they said a reduction in pollution, this is one of their conclusions, may well be a side benefit of increased Mexican specialization and trade. Okay, so don't worry about the environment. It will actually benefit from free trade. And the reason is because Mexico was somewhere around about this $5,000 per capita income level at the time. So the thought was, yes, things are bad in Mexico right now. They'll only get better if the Mexican economy can develop more and get out of that low income environmental trap, so to speak. Why Kuznets curve? Well, this is the original Kuznets curve. It's a relationship between income per capita on this axis and inequality on this axis. So the thinking was in poor countries, everyone is poor. There may be a very small elite, but it really doesn't make a lot of difference. In middle income countries like South Africa or Brazil at the time, there was very high inequality. So a middle class became rich, but most people, 75% of people still were poor. And then in the most developed economies, everyone, very few people remained in real poverty, and the majority were a middle class. And there was a small elite at the top of billionaires and a small underclass of unemployed people at the bottom. Everyone was middle class. There was a lot more equality. And that seemed to be the relationship at the time. This has turned out, this was proposed by Simon Kuznets, who won the Nobel Prize in economics, mainly for his work on national income accounting, inventing the GDP and so forth. Not so much for this idea. But this has turned out to be just as controversial as the environmental Kuznets curve has turned out to be. Maybe it was just an artifact of Brazil and South Africa happened to be middle income countries at the time. Maybe there isn't, particularly as we saw the US become, and some other countries become more unequal in the last few decades, even though as they got richer and richer. Okay, so that's where the word came from. Then in 1992, the World Bank World Development Report was on the development of the environment. Everything was happening very fast in the early 90s around this topic, and they popularized this idea of the environmental Kuznets curve. They commissioned a larger study that looked at various pollutants. We got population without safe water. We got urban population without adequate sanitation. These may be to some degree pollution in rivers, but also that people don't have piped clean water to their houses. But what we saw is that income increased in both these cases. Both these poor environment for people declined. So it was just unambiguously growth would be good for giving people safe water and adequate sanitation. It's probably linked to actual pollution in rivers. Looking at particular matter in cities, they found there was a peak at quite a low level, and then pollution fell. And the thinking there was that smoke in cities is really quite obvious, and when it gets too bad, people do something to clean it up. Then sulfur dioxide, which I already talked about, peaked to maybe a bit higher level, but again, there was this environmental Kuznets curve type peak. So they found for these pollutants, which were more local, there was this inverted U-shaped curve, which fit the environmental Kuznets curve idea. But for some other pollutants like municipal waste per capita, well, it's not necessarily a pollutant if it gets put in a good, well-designed dump, but it is taking up land, using resources that aren't recycled and so forth, requiring therefore more mining and more disturbance. It just increased with increasing income, and carbon dioxide emissions per capita, at least in 1992, also just increased with income. So if there was an environmental Kuznets curve, which they popularized that idea, it didn't apply to these pollutants, particularly carbon dioxide, and it had already happened for these ones. And it was just a few here in the middle which there was a potential to eventually get to falling pollution after a period of worsening environmental degradation. Unfortunately for this story, turning points of a turning point. What we mean by a turning point is the income level at which the curve turns round, rather than the level of pollution at which it turns round. The income level it turns around at. These are studies following on from that period. So Panayotou, 1993, found the peak at $3,000. This is from about 2001. We might have adjusted the values for 2001 prices. Shafiq, that was the World Bank report, was a little bit higher. Torres and Boyce, a little bit higher. Grossman and Kruger's paper actually slightly bit higher, but all these are in the range of 4,000 to 5,000. Then there was Cole et al., Selden and Song, Kaufman et al. List and Galette looked at US states over like a 70-year period, which included Mississippi in 1929 to Connecticut in 1999, or well, maybe a few years before that. So a wide range of income. And they found we had a comprehensive data set covering poor and rich countries, well, states, over a long period. They came up with an even higher turning point. This is our paper published in Journal of Environmental Economics and Management in 2001. We used a data set covering more than 100 countries. Most of these early studies didn't include a lot of very poor countries. And we used income adjusted for purchasing power parity and so forth. And we got even a ridiculously high turning point. So what happens when we look at the data? That was the history. This is looking at sulfur emissions per capita on this axis and GDP per capita on this axis, the average over a 40-year period. And it's a rising curve, in fact, when you look across countries. Now, it does seem the curve gets flatter at these high income levels. We don't really see a turning point. This was in a 2017 paper I published called The Environmental Kuznets Curve after 25 years. So look at the cross-section of sulfur emissions, there didn't seem to really be an inverted U-shape. But for the purpose of these lectures, I thought I must update the data from 2010. And so here you go, this is in 2016. So in 2016, what we find is there is a rising relationship, but what's happened at high income levels has been a lot of divergence. There is a group of high income countries where pollution has fallen quite substantially, back maybe to levels of much poorer countries down here. But there's also a group of high income countries where it hasn't fallen. So there's still actually an upward curve here, but a lot of divergence. Some countries improved, some didn't. With a little bit of imagination, you might imagine there's an inverted U-shaped curve here, but this only happened after 2000 or so, if it is truly happening. When we look at carbon emissions over that 40-year period, 1971 to 2010, we see almost a linear relationship. If you have a lot of imagination, something flattens around here, these European countries in here. But then Australia and the US spoil, etc., spoil the relationship up here. So they seem more linear with the poorer countries, or log linear. Again, updating that data to 2016, we do see the curve has flattened out a bit at the highest income levels. And some countries here have seen the beginnings of a fall in, these are individual countries in a particular year. So this is not evolution over time, but these points have probably fallen from this last curve here as they've grown. So what is going on here? Oh, here's another look. So this was looking at the cross-section of countries at one snapshot point in time, or an average over a long period of time. We generally see a rising curve. But when we look at the evolution of individual countries, particularly in the most recent years, we see something quite different and quite dramatic. So I included here Australia because I'm in Australia. That's the grey curve. I included Belgium because you are in Belgium, and that is the blue curve. And this is from the latest data set just released a couple of weeks ago. Actually, with my first draft of the inaugural lecture, this wasn't. This ended in 2014 and updated at 2018. And of course, there's been quite dramatic moves in the last 4 years in some countries. Yes, it's from the SEDS database, which is produced by the Pacific Northwest National Laboratory in the US. I think that's the group, Stephen Smith anyway. And they do a survey over technologies and energy use and so forth and estimate emissions from that. So these are not official government estimates. These are estimates from an independent group. China, because it's the biggest economy, the biggest country in population, and the UK, because it's the oldest developed economy where the Industrial Revolution started. And it initially, in this period, when it was low income, had the highest emissions in the world. And the US, because it's the most large developed economy, second to China in emissions of greenhouse gases. And what we see is these all follow inverted U shapes. And China, well, in the last decade, they have managed to cut sulfur emissions quite a lot. This is a log scale, of course, after a relatively flat period here, they've sort of rounded the curve and come down here. And Belgium and Britain have almost identical curves and really down. The reason they have identical curves, I think, is because they're under the same policy regime of pollution control across European countries. And the US and Australia seem to be on the same curve as well. Similar economies in some ways. But Australia's lagging behind because, well, I think the real reason why Australia lags is because the population density is very low in Australia, and it's easy to diffuse sulfur emissions in the large amount of atmosphere we have. So it never was as urgent a problem as it was in more densely populated countries, is my opinion. What we see, yes, there's an inverted U. Not all countries, though, go for a turning point at the same point in time. China has turned around sulfur emissions at a much lower level of income. And we saw the same happen in Japan. Japan was one of the first countries to cut sulfur emissions at the end of the 1960s, even though at the time it was relatively poor compared to Europe or the US. So how to explain the paradox of what is going on here? So my interpretation is that at any one point in time, there is a relationship between income per capita and emissions per capita, but really is a rising curve. You're richer, you have more emissions. If any country had unexpectedly high growth in a particular year, we kind of expect to have more pollution would otherwise have happened, we would have predicted at the beginning of that year. Because the scale of the economy is bigger, and there hasn't really been time for technological change to change anything in 1 year. However, over time, improvements in technology lower this curve. So in period 1, the amount of emissions per capita is much along sort of the world best practice line is high. In period 2, it's lower. In period 3, it's lower again. In period 4, it's even lower. So technology improves the world's best practice technology. It improves over time. Maybe only 1 or 2 countries are right on this frontier. Most countries are going to find themselves at higher pollution. So in period 1, all countries are going to be either above or on this curve. Most countries are going to be above the curve, emitting more than the world's best practice. And then over time, the whole group of countries can begin to lower their pollution by sort of following this improving frontier that improves with technology over time. Okay, but if we look at an individual country, it starts off in emissions in period 1 here. It's inside the frontier. It emits more than the frontier level. A typical country, it's somewhere here. In period 2, its economy has grown a lot. GDP has increased from here to here. Its pollution has also gone up. It's still inside the frontier. Maybe by about the same fraction as country 1 was, as it was in period 1 here, proportional wise, percentage wise, maybe just as far inside. Maybe it's actually even approached the frontier a little. In period 3, the frontier's moved down. Its economy has grown more, and it's still inside the frontier. But it's because the frontier's moved down, and the frontier's a bit flatter here, its pollution hasn't increased as much. And in period 4, in fact, its pollution falls as it begins to approach the best practice frontier, and that frontier gets lower and lower levels of pollution over time. And if its growth slowed down a bit, than I've showed here, at the same time as the frontier moved, we would see steeper falls relative to increases in income over time. So this is how the cross-section any one time across countries might look something like this, though we have seen divergence in recent years, at least for sulfur emissions. So it no longer looks quite like a single curve relationship. But an individual country might have an inverted U-shaped curve. There are other reasons also why it might follow an inverted U-shape. If offshoring of pollution was important, which I think it's not that important, it might also contribute to that kind of falling pollution in rich countries, even though there's a rising level of pollution and income across all countries. So can we represent this? Now we're gradually going to get a little much more focused and more technical here. And there are lots of statistical problems with the way the environmental Kuznets curve models were estimated. And so I desired to sort of get around those problems. And I wanted to somehow test this kind of model against the data. And in the IPCC fifth assessment report, which Bernard, the rector, mentioned, I was one of the many authors on the chapter on emissions trends of the report of the third working group 3. They refer to lots of people as lead authors. They like to distribute the honor among many people. But anyway, we were working on the chapter on trends, historical trends in emissions. Coordinating lead author on that chapter was Raya Gerlach, who is in the economist from the Netherlands. And he's told me, hey, I got an idea for your part of this chapter, and it's a very nice graph I just came up with, and I think you'll like it, and I think you should put it into the chapter. And he sent me this graph. And this graph has got carbon emissions. In fact, originally it was total greenhouse gas emissions, not just carbon, and economic growth. And on this axis, rather than the level of GDP per capita, we now have the rate of economic growth. And on this axis, we have, rather than the level of pollution, we have the rate of growth of pollution. And when you plot all the countries in the world, a large selection of countries here, the circles represent how big their total emissions are. So China is up here, very big. The United States is this blue circle here. Blue are OECD, red are East Asia, and then the other regions of the world, Africa and so forth, in other colors. We see here that if you have more economic growth, faster growth in any particular year, or averaging over time, you have faster growth of pollution, of carbon emissions. There's a linear relationship between these two variables. On the other hand, there's some scatter of countries here. And we look at China, its economy grew at 7% a year over this period, but pollution emissions only grew at about 5% a year. So pollution per dollar of GDP or per renminbi fell over time. And that is shown by, if we're on this straight line through the origin, that line has constant CO2 per dollar of GDP, okay? If you are found, these countries here, which are found on this line, countries which are below this line through the origin, they are on lines which cut the axis below zero, so there was no growth in those countries. They actually would have falling emissions. A country on this line would have no growth, would have emissions falling at 2% a year. China's emissions are growing because its economy is growing, but its emissions per dollar of GDP are falling. They're on this line, 2% a year decline in emissions per dollar of GDP. And this line here is 4% per year decline in emissions per dollar of GDP. And we see, in fact, China is not much different to the United States or the European countries, which are most of these smaller blue circles, in terms of its reduction in its emissions intensity. What is different about it is it grew faster. So it was moving up the curve while the curve was moving down. These countries weren't moving up the curve very fast while the curve was moving down. And so they saw flat emissions or even falling emissions in some countries. And this nicely sketches out that relationship in one single snapshot in time. So we thought of an econometric model. I looked at this and I said, wow, this graph is so nice, you should write a paper about it. Eventually, we published that paper in Environment and Development Economics after a lot, 2017, after a long process with some other journals who said they thought it was interesting, in the end said they didn't think it was that important. Here now, instead of the level of emissions or level of pollution we have for the environmental Kuznets curve, we have the percentage growth rate, or the change in the log. So in country I. So this is the growth in country I. And we have its GDP growth, the growth of economic growth in country I. And we're relating the two. And we say there might be some functional relationship. It could be linear. It could be an inverted U-shaped curve, like we saw for the environmental Kuznets curve. We're not wedding ourselves to one model or the other. In fact, we can nest a bunch of different models within this framework. And separate from the effect of growth, there's the effect of time. We said the curve can shift down over time. Okay? And we can also look at which factors lead to that shift down in the curve over time in a particular, and the distance that country is from the world's best practice. So we include a bunch of variables here, which is not really possible in the environmental Kuznets curve framework. Finally, there's an error term. So a growth effect, rate of economic growth here, the rate of pollution growth here, just like in this diagram here, and then the X terms are the ones which are leading you to be on a declining or rising level of emissions per dollar of GDP. So as I said, we can test the effect of different variables on the effect of time. What happens if a country didn't have any growth? What would happen to its pollution? And we can also, by appropriate functional form, test the environmental Kuznets curve idea. What happens at high income levels? Does the effect of growth decline? Does it eventually become negative? Could we have growth that actually cleans up the environment, so more growth results in a fall in a negative pollution growth? Now, we expand this model in this way. This is the growth rate of GDP, and this is the growth rate of GDP multiplied by the level. So this could be positive, and growth initially increases pollution as in the environmental Kuznets curve story, and then later, after you reach some level of income, this term is negative, this coefficient is negative, the effect of growth on the environment might decline. We might actually have a turnaround point, just like the environmental Kuznets curve story. Some of the variables we considered for the X term are the emissions intensity of the economy. The economy starts with high emissions, very high pollution. Maybe they have an incentive to do something about that, as China has found with its very high levels of pollution, to try to cut pollution, to reduce local impacts. Of course, the level of GDP may affect that term as well. Legal origin of countries seems to be important. English legal origin countries, for example, seem to have higher pollution, or everything else constant. Effect of central planning. These countries used to have high pollution in the past. When they reformed their economies, they saw a substantial reduction. Countries have high fossil fuel endowments, like Australia, the United States also, or Russia, may have less improvement than countries that have lower fossil fuel endowments. So the fossil fuels are more expensive in those countries with smaller resources. So it's not the use of fossil fuels, it's how much originally was in the ground at the beginning. Population density and so forth. So look at emissions intensity. This is actually a relationship between emissions intensity and the change in that emissions intensity. The emissions per dollar of GDP on this axis. So it says if you started with a very carbon intensive economy down here, you saw a fall in that carbon intensity over time in a period of 40 years, from 1971 to 2010. But if you had very low intensity, I think Bhutan is one of these countries up here, you in fact saw a very high rise in carbon intensity. So this is a different story to growth is the problem. It says, in fact, if you start very emissions intensive, you are going to, for various reasons, you become more like other countries around the world, perhaps rather than so peculiar, but also you have an incentive to reduce your other pollutants included, and that often leads to reduction in carbon emissions as well. So this is the intensity effect. In fact, it shows and what it shows is a convergence of emissions over time among countries, at least relative to their income level. So countries becoming more similar. There have been some popular models in the economics literature that look at these effects or test these effects versus growth effects. We tested this convergence effect, the growth effect, and environmental Kuznets curve effect, and other variables. There are various advantages of this approach. I won't go into too many technical details here for this audience. Unit roots are the problem of like what economists like to talk about, variables that trend over time, also known as stochastic trends, which is where the name of my blog comes from. We get rid of a large part of the problems you have from these trending variables if you look at growth rates instead. There are differences between countries which are inherent, which we eliminate. Let's be fair, the environmental Kuznets curve approach usually includes those effects and eliminates those differences between countries to try to find a common effect as well. It doesn't look at very short-run changes. What we're looking here at is growth rates over a period of time. So we focus on the longer run effects of economic growth, which I think is desirable. It clearly defines a separate time effect. There's been a debate in the literature about that one as well. And we can test multiple models within one framework. So here is the same graph I drew up for sulfur emissions as well. And for sulfur emissions, the more growth you have, the more your sulfur emissions grow. And this is, again, it's an average over a long period from 71 to 2005. And there's a linear relation. So China had rising emissions in this period, but it had a lot of economic growth. The US had declining emissions, so Europe, particularly declining emissions. This is Europe down here. But Europe and US and China are quite similar in terms of their decline in sulfur dioxide intensity of the economy over time. But because China grew, its emissions grew. And because the US grew more slowly, its economy, its sulfur emissions grew less sharply. So it's below the line through the origin where you have a constant sulfur intensity of your economy. And some countries increase the sulfur intensity of their economy. It's true, most countries reduced it. And that is what we saw with the curve gradually shifting down across all countries over time, okay? But fast-growing countries moving up the curve more sharply and seeing more increase in pollution. So all these results seem to buy into my sort of diagrammatic explanation of the data. There is something particularly special, though, happening with sulfur in Europe. They really cut it more than anyone else did. But the US or Australia, at similar income levels and growth rates, didn't cut it as much. So after the initial paper in Environmental Development Economics on carbon and sulfur, I got a master's student to put together data on all greenhouse gas emissions. By industrial emissions, we mean those are not from agriculture and land use. So this includes carbon from burning fossil fuels. It includes from cement production. But it also includes methane emissions from oil and gas production, chlorofluorocarbons, all these things, all these greenhouse gases. Again, we see a linear relationship between growth and growth in carbon emission, in greenhouse gas emissions, with the constant line here of constant intensity of constant emissions intensity of the economy. Many countries like the US and China seeing a decline in that intensity, and China and the US again not looking that different in terms of the intensity decline, but very different in terms of their growth rates and therefore very different in what happened to their carbon emissions. Then I got him to look also at this guy called Luis Sanchez. I got him to look at non-industrial emissions. These are from land use change and land clearing. It's less convincing, but there's a linear relationship here. But there does seem to be, again, a rising relationship also for land use change and deforestation and agricultural emissions. It's not as strong a relationship as for industrial emissions. Then I had another master's student, Jeremy van Dijk, who's doing a PhD now in Switzerland. And he was interested in concentrations of PM 2.5. This is very small particulate matter, 2.5 micrometers average size, that tends to get into people's lungs and be quite hazardous. Some of it, at least. Some of it is just dust. Some of it is pollution emissions. Again, maybe not the most obvious thing. There is some sort of rising relationship, again, between the growth rate of particulate concentrations and the growth rate of the economy over time. Again, not as strong a relationship as there is for carbon or for sulfur. Now, this delves even more deep technical level, I guess, regression results from these three different papers. So the first paper looked at carbon and sulfur emissions. Another paper looked at industrial and non-industrial or agricultural and forest greenhouse gas emissions. And finally, another paper looked at concentration of particulate matter. Now, the constant is what would happen per year to emissions or concentrations of pollution if there was no economic growth. And for carbon dioxide emissions from energy and cement, that's pretty much a zero. It's slightly negative, but the standard error is almost as big, so there's no significant effect. However, when we look at sulfur dioxide emissions, they decline by about 1% per year over a 40-year period in a country which would have had no economic growth. Of course, most countries did, but if a country had had no economic growth, we have the effect of pure effect of time and shifting the frontier of what is possible down over time to lower sulfur intensities. Industrial greenhouse gas emissions, somewhat different to carbon dioxide. If we include all the other ones like methane and so forth, we actually end up with a very significant decline over time, holding growth constant. And for land clearing and so forth, an even bigger decline, 1.5% per year. For particulate concentrations, it wasn't, at least in this data, some limitations perhaps to the data, there wasn't, only a small negative effect that's not really statistically significant. We look at the effect of growth on an average median country. In the median country, 1% growth in carbon dioxide emissions result in a 1% growth, 1% growth in GDP per capita result in a 1% growth in carbon emissions, everything else held constant in a median country. And very, very similar number for sulfur. So there wasn't a big difference between sulfur and carbon dioxide, despite what the early literature from the World Bank back in 1992 suggested that sulfur was a story of an early peak and carbon dioxide of a later peak or a monotonic relationship. For these for all greenhouse gases, again, a very similar number, just a bit less than 1-to-1 effect. For non-industrial greenhouse gas emissions, land clearing, somewhere around half. So they're much less effective. For particulate emissions, particulate concentrations, effective growth is even smaller, but again, quite statistically significant. But this is the interaction with the level of GDP. So in all of these first three cases and the last case, we see that there is a significant relationship in that richer countries, this effect has become smaller. It's still there probably, but it has become somewhat smaller. And when we look at that, we work out what is the turning point, what is the income level after which this elasticity would actually finally become negative. For carbon dioxide, it's 2.6 million. Of course, that has totally out of sample, and so has a massive confidence interval around it. So basically, it could be infinity, it could be anything. It's some big number. So basically, there was a linear relationship. For sulfur dioxide emissions, 100,000, very similar to our 2001 paper, though perhaps in dollars from a different year, but again, at a high point outside the sample range pretty much. There was no turning point for these because these actually are positive terms for these two. And for particulate matter concentrations, a turning point around $67,000 per capita, which is pretty high income level. So in the richest countries, yes, actual growth might actually reduce particulate concentrations if you're in Norway or somewhere like that. There are other factors, which I've only included a few of the factors in the regression. So countries that saw falling emissions, there are other factors I haven't included. They're included in the regression and not included in the table here, just to have this something that is bearable to look at. So sort of summarizing all of this, on its own, growth doesn't seem that likely for most countries, at least except for some of the richest ones, to clean up the environment. The thing is, some problems, what is good news though, is some problems grow much slower than the economy grows. We saw that like particulate matter or carbon emissions from land clearing. So the economic growth effect is not that big. And we saw the impact of growth, at least for some pollutants, may decline with increasing income, may level out over time. The bottom line seems to be that slower growth in some of the richest countries allows for the other non-growth related effects of policy and so forth and technological change to help clean up the environment. Those countries are growing slower and the curve is moving down, making it possible to have less pollution per dollar of GDP, and they're catching up to that frontier. And the slower they grow, the better. Better they are approached. The faster the emissions are falling, not because of the effects of growth so much, but because of the allowing those other factors not to be overwhelmed or swamped by a high rate of economic growth, which we saw in a country like China. For carbon emissions, probably still, and for sulfur emissions, at least in earlier years. Maybe no coincidence that Chinese economy is now growing slower and they're actually having success in cutting sulfur emissions. Okay, that is really the sum everything up. I think I just about stuck within the time there, so I guess it's time for questions.
Yes, thank you very much, David, for the inspiring lecture. So we had a couple of questions in the chat, so please feel also free to continue asking questions if you have something in mind. So the first question was about the IPAT equation, and the question is whether all of these factors are actually equally important. And the question emphasized that countries like Pakistan and Indonesia, for example, they have very large population. So even if this population remains constant, it could be that habits change. So for example, more meat consumptions, and therefore the environmental impact may increase. So the question is whether this is something that can be predicted within the IPAT equation, and whether this is something one can become proactive about.
Proactive in terms of Stefan?
Yes, yes.
Proactive about.
Well, it's not my question.
Okay, all right. All right. Okay, so population, it's all the factors are just as important as each other in this simple equation. Of course, the terms are growing at different rates. They're likely to have different impacts on the economy. Even we think of it in growth rate terms. In China, the population is growing, but quite slowly. GDP per capita grew very fast, so this was an awfully important term, main driver of increasing impacts. And the technology term we saw was probably somewhat smaller than the growth of GDP, the decline in emissions intensity, for example, for carbon emissions in China. So this term wasn't big enough to outweigh the growth of the economy and result in falling emissions. But in terms of growth, population wasn't that important in China. We looked globally in the last IPCC report, we found that turned out both population and GDP per capita globally had about equal contributions to the growth of impacts. So that's one way of looking about it, how fast each of these terms are growing. another way to look at it is, I think what the question was saying, it's sort of a scale. If we have big P, then even small growth in GDP will have a big environmental impact. So of course, growth in China has a huge impact because it has such a huge population. Growth in Belgium has very little impact because Belgium has a very small population. So, and similarly, likewise, improving technology or behavior through education and so forth. I'm somewhat skeptical, of course, about the ability of us to change people's behavior through, or their preferences at least. We can incentivize them to behave better. If we improve behavior in Belgium or improve technology in Belgium, it has little impact because it's globally, because it's scaling by a very small population. Doing this in China, it has a huge multiplier effect on the world outcome. For local pollutants, of course, it's less important how big your population is. I guess if you have a very high population density, then growth has a bigger impact on the local environment than if you have a low population density locally. So yeah, a bit of nuance on sort of growth and levels and scaling effects. And the positive thing is, if we can get, if China changes its policy direction, which is in the process of doing, it can have a big effect.
Okay, so there was
I hope that answered the question.
maybe the person who asked can use the chat to clarify whether he or she is happy with the answer. And
Sure.
okay, so there is a clarification
Oh,
with regard to proactive. I think you can see it, David.
sure. Yes. Yeah. I think I said yes. It's certainly possible. I think it can have effect on technology term. Economists tend to think sort of incentivizing people by things like carbon taxes or incentivize people to develop new green technologies is going to have bigger impacts than trying to persuade people to behave in an environmentally better way, or persuade some people. Everyone, though, has to use those new green technologies if they become the cost-effective technologies. Okay, next question.
Okay, perfect. Yes, so the next question is also about the iPad equation. And the question is whether it misses key components in terms of comfort and lifestyle. And the argumentation is that once energy efficiency improves, it is also that appliances improve, etc. And so in the end, it might be that energy use actually goes up in developed countries as well.
Yeah, so the energy use goes up. Yes, so I think we'll see in the next week's talk, energy use seems to go up with growth. I don't see a strong picture, but it doesn't really. Again, there's slow growth in some countries, and improving energy efficiency can make actual energy use fall in a few countries, like the United Kingdom. But it was about energy efficiency. So energy efficiency or energy intensity, if this was the so-called Chi identity, we'd have energy use on this, we'd have carbon emissions on this side, we would have population, we'd have GDP per capita, and here we would have energy intensity of the economy. So this is carbon emissions from energy use, energy intensity of the economy, and the carbon intensity of energy. So the mix of different fuels. Energy intensity might improve and have a positive effect in carbon emissions not rising as fast. But if energy intensity falls at a slower rate than GDP per capita rises, then carbon emissions would rise, energy use would rise. What we've generally found across at least a group of countries I'll talk about next week is that energy intensity has improved, it's fallen, less energy used per dollar GDP, but not fast enough relative to the rate of economic growth to actually reduce energy use. So nothing so much, and that sort of lifestyle, it's really probably correlated to the GDP figure number here. I mean, affluence doesn't have to be GDP. It could be some other index of lifestyle or so forth, if you want it. But this is an identity. It has to hold true. The last term is whatever isn't in the first two terms. Okay. Hopefully that
Okay.
will answer the question.
Yes, and would you say, David, this is actually also touching the point of the rebound effect that you will talk about, I think, in the third lecture, right?
Yeah, the rebound effect you're looking at, do energy efficiency improvements, how do they translate into changes in energy use? Well, they probably improve actual sort of energy efficiency in terms of improving technologies. They reduce energy intensity, all things considered, but they make it cheaper to use energy using services. So I think, yeah, maybe the questioner was thinking about the rebound effect, quite possibly. So I will talk about that in lecture 3. Yeah, more energy efficiency means it's cheaper to have a bigger fridge, it's cheaper to have a bigger car, a faster accelerating car, and this may use up some of the technology changes. I mean, iPad again is a accounting identity. It's not a sort of full model of the economy environment relationship. It's a very basic way to think about the relationship.
Okay. So one question that was asked early in the lecture, so I think you answered it somehow already during the talk, is the question whether even if the environmental Kuznets curve would be true, can we actually afford the environmental destruction until the tipping point? It could be that ecosystems might be already destroyed. I guess with a tipping point of 2 million.
Yeah, well, I didn't discuss that in the lecture, but we did discuss that in our 1996 paper on world development, that a small group of countries had moved, the developed economies had moved over the curve, perhaps if it existed, but the majority of countries were still below the peak in the curve because income was very unevenly distributed globally. The average person was down here, even if the mean income in the world was here, the median was a lot lower, and so we expected, according to the 1996 paper, if the environmental Kuznets curve model was true, you would still have rising emissions as the majority of people were still moving up this left-hand side of the curve, and that rise there might well lead to a permanent degradation in the environment, particularly if we look at, say, this curve for deforestation or land clearing and so forth, or carbon emissions that are not totally permanent, but take a long time to revert back to their previous state. Yeah, it's a good point.
So I think there was a follow-up question by the same person, which I think is also very relevant, and it's a question about whether the environmental Kuznets curve should be considered as a at the national level, considering trade, offshoring of pollution, etc. So to what extent does it make sense to look at this at the national level?
Yeah, we've looked at, well, I haven't published a paper on it. I actually was working with, at one point, a PhD student at the University of Lund who was hoping to make that sort of kind of a topic of his PhD, and he found, or at least one chapter of it, he found that when you account for consumption emissions of carbon versus production-based emissions of carbon, it really didn't make a lot of difference to the relationship. There is a difference between the two, but it's not that dramatically big. And if you look at the IPCC reports, you'll see the difference between consumption emissions and production-based emissions when you take into account the effects of carbon embodied in trade are not that big. Again, consumption emissions are the emissions that result from what is consumed, wherever that was produced, versus the emissions that actually occur from burning fossil fuels or whatever within a given country, referred to as production emissions. Yeah, so it didn't make a huge difference. It might be part of the story, but it doesn't seem to be a dominant part of the story.
Okay, there was one last question about the regression table that you entered in the very end of the lecture. And the question was whether you can elaborate that for the carbon emission or carbon dioxide emission equation, the constant is actually not statistically significant. So why is that?
Well, that means the curve hasn't shifted down over time. Growth has a positive effect on carbon emissions, but it's less than 1-to-1. So as your economy grows, you go to higher income levels. For the median country even, you are seeing some improvement in carbon intensity of the economy with that economic growth. That flattens out even more at very high income levels, though it doesn't reach a peak at any time. It becomes flatter. So we're seeing some reduction in carbon intensity that's related to economic growth, but not an inverted U-shaped curve. On the other hand, the curve doesn't shift very much. And if we went back to, well, we looked at this curve over a 40-year period, and we look at this one now. I'm not sure, it's a bit hard to see flashing between them. The argument is that this curve itself hasn't really shifted very much. Countries have moved along it. They've flattened out at the top, so there's economic growth has less additional carbon emissions relative to perhaps at the lower parts here, but the overall curve hasn't shifted down. So there's not some dramatic technology that has shifted the curve independently from economic growth. And that will make sense when we look at what has happened to energy use in the next lecture. The energy GDP curve hasn't shifted almost at all over time, to tell you what one of the main things is there. And the energy mix hasn't really decarbonized that much over time in a dramatic way. So we're looking at carbon emissions from fossil fuels and cement use, that hasn't shifted down over time, even though growth becomes less intensive at high income levels. So we're not seeing any major sort of breakthrough that shifts the curve. I mean, I think those are kind of regression results you can see by looking at the data. You hardly need to do regression, but regression tells you is it statistically significant or not.
Okay, so are there other comments, questions? So maybe we can...
In that speech bubble thing here, the chat, I don't know
yes.
how, I don't think you can see them.
That are the questions that I summarized, yes. So you answered all of them, and persons who asked the questions also indicated that they were happy with the answer. So at this point, maybe I can emphasize that on March 19, there will be a lecture by David then about the role of energy in economic growth. So if you're interested in this, please check out the website at UHustle, the Francqui website. The link was on the first slide. And in these lectures, we expect a small amount of people that are attending the classes, and then we hope also that we can work with switching audio on and off, so that the lectures are also during the lectures more interactive.
Sounds good.
Any words from you, David? Final words?
No, well, thank you. Hope this lecture was interesting and informative, and I look forward to having more interaction in the follow-up lectures.
So thank you very much for the inspiring lecture and for the exciting questions. So I hope you enjoyed this lecture, and I hope to see, or we hope to see many of you on March 19. So bye-bye.
Thank you. Bye,
Thank you.
everyone.
Thank you.